This is part 16 of the series Applications of Differentiation, and in this problem we're looking at a rectangular page is to contain 24 square inches of print. The margins at the top and bottom of the page are to be 1.5 inches and the margins on the left and right are to be 1 inch. What should the dimensions of the page be so that the least amount of paper is used? Let's go ahead and bring up a visualization of this. And so what we have is the margins of the paper, and this represents the text. So the left and right are 1 inches, top and bottom 1.5 inches. So what we're trying to do is we're trying to find the least amount of paper used. So the least amount of paper is going to be area. And so we're going to have to come up with an expression for the area of the page. Now, since the only dimensions we know are these border dimensions, I'm going to have something to represent the dimensions of the text and the dimensions of the page. So let's just call this dimension from here to here, let's call that X, and let's call this dimension Y. Now we know that the area of the print is 24 because they told us it's 24 square inches of print. So I know then that the area of this piece is going to be X, Y equals 24. That's the area of the print. And so we can just put that up here. And now we could come up with an expression for the area of the page itself. So if this is X, and this is 1, and this is 1, this whole distance is X plus 2. And if this is Y, and this is 1.5 and 1.5, then this distance is going to be Y plus 3. So I can come up with an expression for the area of this page. And so the area is going to be the length times the width. So X plus 2 times Y plus 3. So what's going to be our optimization equation? Well, since we're trying to minimize the amount of paper, this is our optimization equation because we're trying to minimize the area of the paper. But again, we have an expression in two variables, and so I need to get rid of one of these two variables. Here we have another equation in terms of two variables. So what I'm going to do is I'm going to solve this one for y and substitute that expression into here before I do my multiplication here. So y equals 24 over x. So I'm going to take this expression and put it in for this. So this becomes x plus 2 times 24 over x plus 3. Now what we're going to want to do is go ahead and multiply through and see what our final equation is. So this times this is 24. This times this is 3x. This times this is 48 over x. And this times this is 6. Now, of course, this is all area. So when I simplify this, we have 30 plus 3x plus 48 over x. So this is going to be the area function that we want to optimize. And so let's take the derivative. dx equals, this goes to 0. Derivative of 3x is 3 plus, this is actually going to be, if I move this over, it's going to be 48 times x to the negative 1. So when I differentiate this, we would have negative 48 times x to the negative 2. And so let's give ourselves a little space here. This becomes 3 minus 48 over x squared. Now we have to go ahead and find our critical numbers to determine what our value is. So we set this equal to 0. We have 48 over x squared equals 3. Then we have 48 equals 3x squared. Divide by 3, 16 equals x squared, and x is plus or minus 4. So here we can eliminate the negative 4, and so our critical number is going to be 4. So let's put that here. Let's try a 3 and a 5 and see if in fact this is the minimum we're looking for. And when we evaluate the first derivative at 3, we find it's negative, and at 5 it's positive, so yes, this is a minimum. And so our x value is going to be 4. 4 plus 2 is 6. And now we can substitute that into here. So we have x is 4, y equals 24, y equals 6. And if y equals 6, 6 plus 3 equals 9. So the dimensions of our page become 6 by 9. And so let's move on to the next problem. In this problem, we have 4 feet of wires to be used to form a square and a circle. How much of the wire should be used for the square and how much should be used for the circle to enclose the maximum total area? So here we have a square and a circle, and the area of this square is x squared, and the area of the circle is pi r squared. So at this point, we're going to have a total area. So our total area is x squared plus pi r squared. But we're also dealing with perimeter because we have to be concerned about using a specific amount of wire. We have 4 feet of wire that we can use. So we're dealing with perimeter. So perimeter is x plus x plus x plus x. So the perimeter is going to be 4x plus the circumference of the circle, which is 2 pi r. Now we know the perimeter is 4. The total of this has to be no more than 4. So 4 equals 4x plus 2 pi r. And we know that we're going to have to optimize our area. So this is going to be our optimization equation. So what I want to do is I want to replace that r with some expression for x. So this is the natural equation to solve for r. So 4 minus 4x over 2 pi equals r. So all I did was I subtracted 4x from both sides, and then I divided 2 pi by both sides. So now I have my expression for x, which replaces my r, so I can replace that down here. So area is x squared plus pi times 4 minus 4x over 2 pi. And this whole thing has to be squared. So now we're going to have to simplify this. So I can take out a common 2 out of here. So we have x squared plus pi over 2 minus 2x over pi squared. So let's go ahead and factor out a 2 out of this numerator. And so we have area equals x squared plus pi times 2 times 1 minus x over pi squared. Now I can square both of all these terms in here and make it a little simpler. So area is x squared plus pi times 4 times 1 minus x squared over pi squared. These pi's cancel out, and we have x squared plus 4 times 1 minus x squared all over pi. Now we should be able to differentiate this. So dA dx equals 2x plus, pull out the 4 over pi, times 2 times 1 minus x times the derivative of the inside, which is negative 1. And so this becomes 2x minus 4 over pi times 2 minus 2x. So let's go ahead and distribute this 4 pi. So this gives us 2x minus 8 over pi plus 8x over pi. Now we can group these two terms together, and we will have 2x plus 8x over pi minus 8 over pi. Now we can factor out a 2x out of this, which should give us 2x, and we have a 1 plus 4 over pi minus 8 over pi. Now let's go ahead and set this equal to 0 and move this to the other side because we're looking for our critical numbers. So we have 8 over pi equals 2x times 1 plus 4 over pi we'll divide both sides by 2. And let's simplify this a little bit, see what happens there. We get 4 over pi equals x times pi plus 4 over pi. And we can multiply both sides by pi and get rid of that pi there. So we have 4 equals x times pi plus 4. And now we divide 4 by pi plus 4 equals x, and that comes out to approximately 0.56. So that's our critical number. Now, since they gave us 4 feet of wire to use, that means we have a closed interval, because a reasonable domain for this function is going to be 0 to 1 for x, because 1 plus 1 plus 1 plus 1 is 4. So if we used all the wire for the square, then we would have 1 for x. If we use none of the wire for the square, then we'd use 0. So we need to find the maximum of f of 0, f of our critical number 0.56, and f of 1. This comes out to 1.27 approximately, and this comes out to approximately 0.56. That's a 5. And this is equal to 1. So here we have our max. And we can see that a maximum area comes out of using none of the wire for the square, which means all the wire is going to be used for the circle. So this was a good example of extrema on a closed interval. And so let's see what the next problem has in store.